Chapter 4, two-dimensional kinematics, including projectile motion, relative velocity, addition, and kinematics of circular motion. So we'll start out by doing some problems similar to what we did in chapter 2. For example, the problem that we did where the car was going, let's say, to the right, and then from there the car was going to the left. So you see this was a one-dimensional motion, and we asked what's the average speed, what's the average velocity, what's the average acceleration, right? We did stuff like that. So now we'll do similar one like that, and then we apply it to two-dimensional motion. And then the other one we'll do is similar, a little bit similar in style to the one that we did where I gave you a position function as a function of time. Then you took the derivative of that, you got the velocity. You took the derivative of that, you got the acceleration. And then we answer things like what's the average velocity, average acceleration, all of that stuff. Then we'll transition into projectile motion and cases where the acceleration is constant. So constant acceleration motion. Right? And then we'll dwell on that, and then projectile motion is kind of a subspecific set of that. So it's an example of a constant acceleration motion. Then probably this will go into next week also, where we deal with relative velocity addition and then circular motion, kinematics of circular motion. Okay, so the first problem we'll start with, it will kind of tie into circular motion. So we'll say a car is going in a circle of radius 30 meters. Car is going in a circle of radius 30 meters with a constant speed of 40 meters per second, and it starts So a car is going in a circle of radius 30 meters with a constant speed of 20 meters per second, and it starts at an angle of 20 degrees west of north and moves in a clockwise direction for 8 seconds. So see, there's a lot of details there. Some problem like this, you have to underline, circle important key words that will help you draw the correct picture of this, right? And then based on that, it's going to ask you a bunch of questions. Like you can say, what is the distance traveled by the car what is the average speed, the average velocity, and the average acceleration, what is the initial speed, the final speed, the initial velocity, the final velocity, the initial acceleration, the final acceleration. There's the distance traveled by the car, what is the displacement vector, what is the initial speed, initial velocity, acceleration, initial. Yeah, I think that's pretty much most of the questions, because if you can answer this, then you know everything about that. Right?
So for the question B, it's asking for the initial, right?
No, average.
Average.
This sign is just a short way of asking average.
Oh, okay.
And then since this is not a vector, I don't put a vector sign here, but for velocity and acceleration, I put a vector. Okay. So it all starts with drawing the correct picture. What does the picture look like? Okay. And if you got the picture wrong, then of course it's gonna throw it off. So it starts out 20 degrees west of north, so right, remember north was this way, west, so something looking like this, right? The radius of the circle is 30 meters, car's going this way, right? Which way is the car moving? Clockwise, so that it's driving like that. This is your initial velocity. Right, so the car is going like that. Make sense? Right, so if you got that picture wrong, everything else, a lot of other things you would do after that would be wrong. So this angle here is 20 degrees. Right? So then what is the distance traveled by the car? Right? How do we calculate that? Well, it's going at a constant speed, right? 20 meters per second. Then just multiply that by 8 seconds. 160 meters. So the distance it travels is 160 meters. What is its displacement vector? So now the displacement vector is a vector that starts where it began and where it ended. Well, we don't really know where it ended now, right? So where did it end? 160 meters. So how do we find out where the final car, where is the car at the end? After 8 seconds.
Like we calculate how long the 160 meters counted as the perpendicular.
In terms of angle?
Yeah.
Right, because 160 meters is the distance along the circle, right?
Yeah.
So then we don't know, does it end here, does it end here, does it end here, or does it go a full circle, right? So let's calculate the circumference. 2 pi r, 2 times pi times 30, 60 times 3. So it looks like the circumference is about 180.
In radians, right?
No, it's going to be meters. The radius is meters, so it's going to be distance. It's going to be units of meters.
188.49.
188 0.49 meters. So the a complete circle would have been 188 meters. So he's almost going a complete circle. So that means he's going like this. My circle looks bad. So whole circle would have been 188. So he's going a distance of 160, right? How can I find this angle, the final angle? Can I divide the distance that he went by that and get, that would give us radians, right? So x divided by the circumference. See, this is in meters and that's in meters. When you divide meter by meter, what do you get? Radian, right? Because radian is a unitless unit, it has no unit. So that's almost
0.84.
No, sorry, I said it wrong. This is not a radian. 60. Because the whole circle would have been 2 pi rads, right? So how many radians did he travel? He traveled this, because if this ratio is 1, that means he went 2 pi radians, right? So I have to multiply this by 2 pi to convert it to radian. That's how many radians he traveled. The distance that he went divided by the circumference times 2 pi. So he went slightly less than 2 pi rads. Or I think in this problem, since we're working with degrees, it's better to just to multiply by 360.
Yeah.
Okay. What is that?
You want it in degrees,
In
right?
degrees, yeah.
305.57.
0.57. So what does that mean? Well, that means starting here, he went all the way 305.57. That's how many degrees he covered, right? So if I want to know, let's say, just this piece, right, what would that be? This portion is 20, and then this whole portion is 270, right? So then subtract from here 20, which accounts for that, minus 270. So basically subtract 290 from 305, which will give you 15 degrees. So that means this little piece is 15. So my drawing can be better. Something like that, right? .57 degrees, right? And as he was traveling, the shape of the car changed, it got thinner, because relativity, right? It says that when objects travel near the speed of light, they get thinner, right? No, that's just a joke. So far, so good. So what is the displacement now? Displacement is the vector that starts where you started and goes all the way to where you ended. This is the displacement. So it's a downward facing vector. So now give me the magnitude of that vector and the direction of that vector. What would that be? Yeah.
207 degrees. Where did you get that
Which one? 270?
from? Yeah, 270.
Oh, because from here to here, he's asking where did I get the 270? From here to here was 20. Then this is 90, 180, 270. Right? So the total angle from here all the way to here would be 295. Right? And then the rest of the piece is the 15. Okay, so what is the magnitude of the displacement vector? Which would be the length from here to here. I think this one we can do it more easily if we use some geometry, right? This is an isosceles triangle. Looks like this. This is 30, which is the radius, right? 30. This is also 30, right? How can I find that distance? Do we know this angle?
Yeah.
20 and 15, subtract that from 90, so a lot of geometry in this problem. Geometry trig. 90 minus, right, subtract 20 from that. Subtract, and then subtract 15.57. So this piece is 54.43. So how do I find D?
So we can use that formula cosine.
Law of cosines?
Yeah, so a squared is equal to
Yeah, so this squared is equal to
b squared plus c squared
minus.
minus 2bc times cosine that theta.
Okay.
So we can solve that.
Yep. You could probably factor out this one, make it a little easier. Factor out the 30 squared, right?
Yeah.
Then what will you have? 1 plus 1, 2 minus 2 cosine 54.43. You can also factor out the 2. And then square root both sides. Square root of 2 so magnitude of D will be square root of 2. So I cleaned it up by factoring out the 30 squared, added 1 plus 1, 2. Then there's another 2 here, factor that out. Square root of 2, and then 30, and then 1 minus cosine 54.43, square root of that.
$27.43.
Okay, 27.44
Yeah.
meters. So essentially, he only moved 27 meters effectively, right? Because he almost came back to his starting point, right? So even though the distance he covered was a lot, the displacement is very little. Because if you go around the whole circle, your displacement is 0. And how about the angle? So by the angle, I want to know the angle, this angle of the vector from the x-axis. Right? Consider this the x-axis right here. Right? So what is this angle? What I can do is if I know this is 54, I could find out this angle, right? Which is going to be this angle. So what would this angle be? Well, these two angles must be the same, right? So 54, so 180 minus 54 over, right, divided by 2, right? What is that going to be?
62.78.
62.78, 62.78. Right? This is like 9th grade geometry all over again. Everything.
How do you know that both of those are the same?
I saw same length. Right, 62.78, 62.78. So if that's 62.78, what is this? Let's see, how are they related? It's probably related to this being 20. Right, if that's 20, then what is this? Well, this is a 90-degree triangle, right? Right? So if that's 20, this is 70. True? If that's 70, and now we know that this is 54.43, right? So if that's 70 and this is 54, what is this? Oh, gosh. Beautiful. Yeah, 180 minus 70 minus 54. Awesome. A simple path of a car in a circle became so complicated and beautiful at the same time, right? So what is that going to be?
55.56.
Okay, so then you just go, this angle theta is 180 minus 70, which is 110, minus 54.43, 55.57.
Yeah.
Right?
Yeah.
Yeah, makes sense. So then we would say the displacement vector has a magnitude of 27.44 meters, and its angle is,
Sorry.
yes,
Didn't we say that angle was 62.78?
which
The
angle?
one right next to the 70 degrees?
This one?
The one right next to it.
This one?
And that's 52.78.
Oh, yes.
Wait a minute, where did I get 54.43?
That's the yeah, that's the other angle. That's the top
Oh,
one.
yes. How did I miss that?
Oh.
So this is 54.43. This is 62.78. So 180 minus 70 minus 62.78. Of course, all those mistakes I make, I'm making them on purpose. Right? I'm showing you the typical mistakes students make. Those are all calculated. Right?
Yes. 47.
See, he believed me. That's what matters. It's
Yeah.
not the truth, whether it's the truth or not. It's whether you can make people believe you. Let's see, 40. What? 7.22.
62.78. That angle
Okay.
62.78. Okay, I see.
47.22 degrees. Since the original angle of the problem was given in west-north direction, so this one I'm going to do it as a west-north, right? So what should we say here? West of south or south of west, or how should I put the angle?
West, north, south of west.
Yeah, it's a bit tricky, right? Northwest, and you're starting, which one should I do, right? This one is,
South of
since this one, it's west and a south of west, right? South of west. There you go. That's the displacement vector. 47.44 meters, 47.22 south of west. So that utilized quite a bit of the law of cosines. There was some radians there, degrees that you had to do correctly, a bunch of geometry there, quite a bit of stuff from geometry. And then we've only answered A now. Okay, what is the average speed? Average velocity, average acceleration, And if we want, we can answer these at the same time. I mean, it's up to us which one we want to answer first. For this problem, these questions are going to be easy, the average speed. The initial speed is going to be easy because the car is going at constant speed, right? So the initial speed and the final speed are the same. What is the speed? 30 meters per second? Oh, 20 meters per second. So initial speed is 20, final speed is 20. What's the average speed? 20. Anyone have questions? I think, Jonathan, you look like you had a question.
No, that's weird.
Yeah, just ask. Nothing to be. We're all here asking questions. You got it?
What's the theta for?
Huh?
What theta that we found right there?
It's the angle of the displacement vector. Because to be a vector, you need to show the direction of the vector and the magnitude. So basically, you're saying the car ended up 27 meters from where it began at an angle of 47 degrees south of west from where it began. That's what that means. The distance is just saying the car traveled 305 meters, but you have no idea what does that 305 meter mean. Did the car travel in a straight line? Did it go in a circle? Did it do a loop? You know, so the distance doesn't tell you what the car actually did. It just tells you how far it went. But the displacement tells you, okay, it ended up there, you know. Somebody else said that.
I was gonna ask for the speed, but I copied it right. It was 20.
Was it 20?
Yeah.
Yeah, 20. So in this kind of a problem, if the average, if the problem tells you it's constant speed, you already know the average speed and the initial speed and the final speed are the same. Okay, how about initial velocity, final velocity, average velocity? Well, average velocity is going to be pretty easy. Why? Because it's the displacement divided by the time. So all you do once you find the displacement vector, take this divided by the time, and then the angle is the same as the displacement angle. So 27.44 meters. So the magnitude of the average velocity is going to be 27.44 meters divided by, was it 8 seconds? Yeah. 8 seconds. So it's going to be 3.43 meters per second. And the angle of the velocity is going to be the exact same angle as the displacement. 47.22 degrees south of west. There you have it. Okay. So, yes. Huh? Versus west of south? He's saying, why is it south of west? Would you want to flip those? You would say, you want to say west of south?
Because there was west of north.
Oh, yeah, the original direction was west of north. This angle, that's the position of the car. But then this angle, this one goes here, then you go this vector, it's this angle. So this angle and this angle are not related at all. The first original angle that was given is the angle of the position of the car. The angle we found is the angle of the final position with respect to the initial position.
Okay, so you're saying that is where the car is?
From where the car originally began, right, which is here, to where the car ends. Right? So let's say the faucet is the origin. I start here, some random position. Then I walk like a weird position, right? And then I end up here. Okay, so what's my displacement vector? And what's the initial position vector is this guy, right? Like that. And then that angle, that's the position, right? And then if I walk this way, and then end up there, so my displacement vector is going to be like this, straight line to where I ended up, right? And then the angle is going to be this angle. You see? Yeah, so you can always define a certain origin, and then you start walking around, you know. and then your original position is going to be that. So what's the meaning of this one? The meaning of it is that while you were taking this path, if there was a person walking, or you're going to say, oh, you know what, I want to go in a circle. I want to test out my car, for example, around a turn. And then you say, there's a coffee bar there, let's meet there. So then this person walks, and then the car goes around at 8 meters per second, you know. And then this person can walk straight there. So how fast do they have to walk? 3 meters per second in order to both get there at the same time. So they don't have to walk as fast. See? Where the car has to go 8. Okay, so now the initial velocity is going to be what? Well, that's going to be this velocity, right? And its angle. What is that? So what's the magnitude of that velocity?
That's 20.
That's 20 because it's equal to the speed, right?
Yeah.
So the initial velocity is 20 meters per second, but then what is its angle?
20.
Is it 20? Is it the same as this?
Yeah.
No.
Okay, how do we know for sure? This is a 90 degree, is that a 90 degree angle?
Yeah.
The velocity is tangential to the circle, right? So the position, and then this is the velocity. Yes, that is 90 degrees. See? So if this is 90, and this is 20, we already said this piece is 70, that piece is 20, right? So yeah, it's always nice to start clean here. Make sure you're, this is V initial, this is 20, this is 70, this is 90, this is 20. So yes, 20 meters per second at 20 degrees. That is the answer. So the average velocity, the initial velocity is more like the initial speed, whereas the average velocity is way different, right? So it's basically the initial speed and then the angle of the speed, basically. The final velocity is going to be 20 meters per second at what? Then it's going to be at an angle of whatever, let's see, this angle, right? Yes, because it has direction and magnitude. Yep, you got it. So then you go like this, you go like this, then you go like that. Right? So it's like this. I'm just going to redraw it here.
Professor.
Yes.
For the initial velocity, after the angle doing that to the side, so that one is north of west.
Yeah, you could, yeah, definitely. You could say north of west. Yes. And then this is going to be, so now the final velocity is going to be what? We found, remember this was 15 degrees. So we want to know now this angle, theta final, V final. What is that?
90,
15.
90 degrees
This is also 15.
divided by 15 point.
90 minus 15, right?
Yeah.
Oh, okay, yes. Yes, which makes sense because this angle is larger than that angle, right? So then we can say that 90 minus 15 is going to be what, 75? 75.33?
74.
Huh? 90 minus 15.57.
Yeah, 74.
43, right?
Yeah.
I'm trying to do it in my head, you know. Is that right?
74.47. 43.
Oh my gosh, right. Yes. 74.43 north of west.
Those aren't averages, right?
Nope, sorry. These aren't averages. They're just vector size. Initial velocity, final velocity. Yep. And then this is average, so there's a bar over it. So we pretty much are done with that. Now we just have the accelerations to do. Initial acceleration, final acceleration, and average acceleration. Let's see here. How do I do the initial acceleration? Question?
Yeah, but should they be north of east?
North of east.
Who told me north and west? I was just going by what they were saying.
I just told you the angle. I just told you the angle. I didn't tell you the
Right.
Oh, no, not this
He's
one.
like he's washing his hands. I just told you the angle. I trusted you. You let me
Alright.
down.
I'm still.
Come on, Anakin. You let me down. I trained you.
Well, that's the reason we train you one row, right?
Huh?
That's the reason we gotta train, right?
Yeah, I know. Yeah. That was from the third Star Wars.
Yeah.
Anakin, what happened? Okay, so initial acceleration is going to be what? Since you're going in a circle, your accelerations are towards the center, right? Centripetal acceleration. So your initial acceleration faces towards the center. Your final acceleration faces towards the center. Because when you're going in a circle, you are experiencing what's known as centripetal acceleration, right? It's always towards the center. What's the magnitude of the acceleration? Remember from physics 11? The speed squared divided by the radius, right? Right? The magnitude of that is the speed squared over the radius, right? The initial speed squared over the radius, but the speed is never changing for this problem, so it's just 20 over the radius. So what's that? 13.333 meters per second squared. Right? Is that right? 20 squared, 400 over 30, yeah. Meters per second squared. And what's the angle of it? Initial acceleration. So now, how do I find out the angle of a vector facing towards the center? Well, it's this angle, right? 70. Right? 70 degrees. And how should I word it? 70 degrees, what? North, south, east? Yeah, 70 degrees south of east. So that means if that vector, you place it at where it began, that vector 70 degrees south of east will face towards the center. That means it's centripetal acceleration. It faces towards the center. Okay, the final acceleration.
Oh, this is something weird.
Huh?
Oh no. Oh yeah.
What is it?
Yeah, never. I realized.
And then the final acceleration is the final speed squared over the radius, which isn't going to change. It's going to be the same still. At what? Now it's also going to face towards the center. So it's going to be like that. So now we need this angle. 15.557 south of east. Yep. So you see how kind of chapter 4 is more of an application of chapter 3. Still like almost like chapter 3 is continuing. It's continuing to haunt you day in and day out through chapter 4. So all that vector stuff, you really got to get it down. Okay, how about the average acceleration? And for average, you always do what? V final minus V initial over the time. So you're taking the final velocity of the object, subtracting the initial, well, we already know the final velocity is this, right? and this is the initial. But we have to break it into components in order to be able to subtract it, right? We can't subtract 20 minus 20, right? So how do we express this? What's the final velocity? 20 cosine of 74, right? 0.43 I hat, right? And then 20 sine of 74, because it's in the first quadrant, right? So since it's in the first quadrant, the angle, I don't have to change it at all. I can keep it as 74, and the other one is in the first quadrant too. So 20 cos 74 plus 20 sine of 74 j hat minus, what's the initial velocity? 20 cos 20 I hat plus 20 sine 20 j hat. All of it divided by the time, which is 8 seconds. Okay, so now how do we subtract that? Now in order to subtract it, you combine the I components, then you combine the j components. So 20 cosine 74 minus 20 cosine 20 I hat. So I'm subtracting this minus this. Then I'm going to add to that this minus this. 20 sine of and divide this by 8 seconds. Divide this by 8 seconds. So you divide 8 into both of them. Sometimes over here I've seen students do this. They'll put a minus here. What are they confusing here? What's wrong with the minus there?
That makes that first.
Yeah, because they're looking at this, you see. They're getting confused with that. But then this minus this is that, right? Plus this minus this. So this one will create a confusion. Minus minus is a positive, right? So you have to do plus this minus this. Okay, so now calculate what that gives you.
Minus 1.678 I hat
Minus 1.678
678
I hat
plus 1.55 J hat
plus
1.55
1.55 j hat meters per second squared. Now we can turn that into a magnitude and direction. What's the magnitude of the average acceleration and its direction? So we got it. This is called unit vector notation. So if I tell you, give the answer in unit vector notation, you leave it like this. If I say, find the magnitude of the average acceleration, then you do this squared plus this squared square root, right? You turn it into a magnitude. So you're going to square 1.678 plus 1.55 squared, then square root of that.
You said that's vector notation?
This is unit vector notation. Unit vector notation. Because ij is unit vectors. And this is the magnitude angle notation. Magnitude angle. So the magnitude is square root of 1.678 squared plus 1.55 squared. Okay?
2.286
2.286 meters per second squared. Angle?
Negative 42.72.
So how should we word that in terms of northwest?
South, west of south.
West of south. So say that again. 42.
Negative 42.
Yeah, but you don't want to put
Oh, you
negative.
want to put it.
42.72 west of south. Okay, so as not to be confused, what should you do? Always quick picture. Otherwise, you're just guessing in the air. Right? This is negative 1.6, 1.55. So the acceleration vector looks like this. The average acceleration vector. Right? This is negative 1.678, 1.55. So what does the negative 42 mean? Well, negative 42 is going to be in the fourth quadrant, right? So it's going to be in the same thing as this. 42.88. Okay, now you can visualize how to say it, right? 42.88 north of west. Because otherwise you're just guessing in the vacuum. Oh, negative, and then you're just like lost, you know. You have to visualize the x component is to the left, the y component is up. When you do the tan inverse of that, it's going to give you in the fourth quadrant, right? But if you want to express that in terms of northeast, you just say, okay, this is negative 42, which is going to be the same thing as this guy, which is 42. So then it's going to be 42 north of west. Did I say that right? Yeah.
West of north.
No, west of north would be this one, which would be 48 or something, 47. 42 is this piece. West of north would be, if you want to give this angle, which then you have to subtract this from 90. You can say 47 degrees west of north. Okay, try to review everything we've done. I'm going to give you a little break because you're probably so busy writing. So look back from the beginning of the problem, how I calculated the distance, the displacement, the angle, see if you have reviewed the whole thing.
So maybe no, I mean probably computers are
I'm not swearing it, I don't care. Oh, because the chart, you see, if I want to figure out the angle, when I'm squaring it, I don't care.
Oh,
But if I want to figure out what angle is in north of west, east of north, I want to draw the vectors like
yeah, here it is.
One,
Cosine, I'm like 20
and if it's negative in the x direction, and it's positive in the y direction,
43 and minus
in order to do that. Otherwise, you'll be looking at that vector and then you won't know whether it's south, south or east.
Subtracting like this, 60 subtracting like that. This is, anywhere in here.
It's gonna be in this one, there's no tangent.
Like up to here, I was there, and then at this point, I was like, Is that a right angle? I mean, like, you do the right angle. Why are we looking through that little piece? The x-axis and whatever is not 70 degrees.
Because it says in the source there's 1 to 3
I guess that's the way the car's pointing. That's where the car is. That makes sense. That, but then, where are all these other angles? Because they're the x-axis, not the circle. Depending on where it's and then this whole like this.
Was like that. And then
converting it. Then I'll make this chart. I'll make another chart and then in reference to that. Without making a mistake. Line that ruins the whole problem.
Have a form of calculation, like using a calculator.
Yeah, never let the entire
Doing the math, for this part, is there like 20
cosine, yeah.
I get a different answer.
Are you in degree mode?
I don't know.
Mode. See your radius. Go to degree, and then quit, and then press.
Okay.
Is that what the answer is? Yeah,
Yeah.
1-1.678. Yeah.
Okay, yeah. How do I set this one? Like
Mode.
mode?
Go down to the radian degree. Yeah. For these sections, you're gonna be purely degree.
Yeah. Oh, it's a formula.
Yeah.
So,
Or just quit. Question?
Where did we get like that?
Tangent inverse of. I can write it down.
Yeah, sorry. Like, as I was writing it down, I just looked up and there was a number. And I was like, I don't remember where we got that from.
This one was, he's asking where did the 42 come from? It's tangent inverse of 1.55 over 1.678.
y over x. Y over x.
Yeah, it's a negative degrees, but you just plus 180 to get a positive.
Yeah, on this one, I didn't plus 180. I just wrote it as 42, but wrote it northwest.
Yeah, no,
Yeah, we do.
So
because I
1.6.
theta is in quadrant 2.
Yeah,
So
quadrant
that's
2.
why it should be 137 degrees.
Yeah, there's a lot of analyzing in these chapters. Which quadrant am I in? Is it west? Is it south? Is it first, second, third? All that stuff that you might have forgotten.
You still put the negative in the tan inverse.
I could put a negative, or I can just do the absolute value.
But then you just.
But then I analyze what quadrant it is in and figure it out from there.
Okay.
Yeah. Notice one thing from here, that the average acceleration has a magnitude that is a lot smaller than the instantaneous accelerations. Right? Why is that? See, instantaneous acceleration is a measure of the instantaneous forces on the car, right? So the instantaneous forces, boom, 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 boom. So in order for the car to make a turn, a force is being applied on it inward, and usually it's being applied by the friction force of the tires with the road. That's allowing the car to make the turn, right?
Right.
So it's the instantaneous force. But then if you take all that vectors, if you take all these vectors, some of them are canceling each other because they're in opposite directions, right? Yeah, so basically a lot of them are canceling, and so only sort of the average of all those vectors are remaining. You see what I mean? It would almost kind of like if I said, everybody come over here and punch me from different directions. because you probably want to do that right now, right? So everybody punch me, right? And because you're punching me from random directions, all your forces cancel. Well, I don't know if that would happen. I think it would be worse, right? But my head wouldn't go back as much, right? Because it would kind of cancel, so it would stay in place. It wouldn't move as much, right? So, but the force I feel would kind of add up, right? I don't want everybody punching. Right. Now, how about the angle? Look at the angle. There's something gonna be surprising about this angle that we got. Look what's gonna happen. Because the car is going at a constant speed, and since all the instantaneous accelerations face towards the center, I'm gonna venture to propose that the average acceleration should also face towards the center. When the average acceleration is placed at the midpoint of the route that the car took. Do you see my argument? Do you think that that's a valid argument? So if I'm going at constant speed around the turn, all the instantaneous vectors face towards the center. Now if I take my midpoint and I place my average acceleration there, then it should also face towards the center, because all the instantaneous ones face towards the center, right? So let's locate our midpoint here. You're starting at 20 and you're ending up at 15.57. The total angle you were traveling was what? 305, right? So if you divide 305 by 2, this number by 2, you get 152 point something. After that, my brain freezes up. What is it? 7.5? 7.85? 152.785, right? So then, if I measure, okay, you start at 20, 152.785, where is that going to take you? Okay? Where's the midpoint going to be? So then what should I do? Where is the midpoint going to be? So what I could do is subtract 90, subtract 20 and 90, and then find out what's this missing piece that I need, right? Let's see here. Subtract 20, and then subtract the 90. That gives me what? 110, which is going to be 42.785. So my midpoint is like right here. And its position is such that it's 42.785 below the x-axis. See? That's my midpoint of the route taken by the car. Now, if I place this average acceleration vector, this one, negative 1.678 plus 1.55, if I place that at that point, negative 1.678, 1.55, and so the average acceleration vector is pointing this way, right? How can I prove that definitely it's facing towards the center? Its angle should actually equal 42.785, right? So this missing piece was 42.785, and the angle we got for the average acceleration, 42.72, right? Did we prove it? Well, you might say it's not exactly the same. That's because of the curvature of space. Space is curved due to general relativity. No, that's not. It has nothing to do with that. It's rounding errors. Made it sound so much better, right? Okay, yeah, so it was just rounding error. Right, so 42.72, that was the angle of the acceleration. And the position of the midpoint, if you place that there, so now you can kind of know the physical meaning of the average acceleration. It's the average of all the forces on you, such that if you're going at a constant speed, your average position is at the midpoint. Then the average acceleration should also face towards the center, therefore. You see? Nice, nice. Okay, now let's do the other type of problem where I give you the path of the particle in terms of an equation. So the things that I'm having you calculate are the very same exact questions. I'm saying find the distance traveled by the particle, displacement vector and its direction, find the average speed, the average velocity, the average acceleration, and then find the initial speed, the final speed, initial velocity, final velocity, initial acceleration, final acceleration. So same exact questions as we asked about the car going around the circle. This time, however, you're given the path of a particle in terms of a certain general equation. What are these kind of problems called in calculus? Remember those? I think you might have done them in Calc 2.
Variation of parameters.
Variation of parameters? Weren't they also
Parametric
called
equation.
parametric equations? So parametric equation, because what's happening here, the position of the particle is some position y as a function of x, but then x is also changing as some function of t, which means y is also changing as a function of t, right? So, so you've got something like this, two-dimensional motion. So you have x. So it starts out here, huh? And then the particle is moving to the left. So it goes like this, like that, and then it ends over there. So this is your V initial, right? That's your V final. So this is the equation x equals y squared, so it's a parabola that opens to the right, you see, like that. So then you have some kind of general function x of t. Remember when I was first giving you the x of t equation, I wrote it without the 4, but then I added the 4. Why? Yeah, because you have to match, the equation has to match what's happening in the problem. So if you put t is 0, it tells you the particle starts out at x equals 4. So if you put t is 0, that means the particle starts out at x equals 0. See? So you need something there that will make the particle start out at 4. Well, you know what? This is a bit tricky because it's not matching. My x of t is not matching what's happening. This isn't matching what's happening here. Here the x is decreasing, right? And then increasing back. This one makes it look like it's all increasing. So they're not matching what is happening. So what should the problem giver give in order to make it realistic? The y position of the particle is increasing along the y. So probably you can do something like this, which makes more sense. Y of t is, let's see, would that work? Would that work? If I gave you a function like that? So then the y would start out, when t is 0, would start out at -2. And then as t gets bigger, y would increase. Yeah, I think that would match, right? Yeah, I think that's going to work. So -2. And then the x would be the y squared, which would simply be this thing squared, right? Yeah, okay. Yeah, it's working. Okay, so how do we find the displacement? I think the easiest problem to solve here is the displacement vector. Right? What is that? It's the vector that starts from where you started to where you ended. Right? Your effective displacement. That one takes the least amount of work for this problem. So this position is what? 4, -2, and then this is what? 1, was it? 1, 1, right? So you end here, so it's 1, 1. So what's your displacement? 1 minus 4 and 1 minus -2. So I can get the displacement by just simply doing the subtraction of its final position minus the initial position. Right? Displacement is the final position vector minus the initial position vector. So 1 I hat plus 1 j hat minus 4 I hat minus 2j hat. 1 minus 4, negative 3. 1 minus minus 2 plus 3. So that's the displacement vector. Yeah. What I'm, oh yeah, you're right. This one was the velocity vector. So this vector I should put to where you're ending. Yeah. And then this thing is the final velocity vector. And then this is the initial velocity vector. So that's it, negative 3, is that right? Negative 3 plus 3, right? So if I want to, that would be unit vector notation, right? Unit vector notation. And if I wanted the magnitude of it and its angle, what would I give? The magnitude of the displacement would be what? 3 rad 2 at an angle of what? Yeah, that would be 45 degrees north of west, right? So that would be 45 degree angle. So that was pretty quick. Average velocity would also be easy because it's just simply the displacement divided by time. Oh, but we haven't found a time really, right? Okay, so that's the next thing we should do is find out how much time, because a lot of things are going to rely on us knowing the time. How much time does this trip take? How would we do that? Put y of t is equal to what? 1, right? So for t. And then once we get the time, we can answer a bunch of other questions. So put this y equals 1, and then you would get what? T squared plus 3t cubed minus 3 is equal to 0. Put that in the solver on your TI. Put it in solver. Solve for that. Go to math. Huh? No, we haven't even found the distance. No. So far we've only done the displacement.
Point 0.9?
0.9? 0, 0?
Yeah.
Exactly?
Yes, sir.
Well, that's weird. And that's just one answer? Okay. Okay. Okay, from there I can calculate the average V, the next one, easy. So the average V is gonna be the displacement, which is 3 rad 2 divided by 0.9 at an angle of 45 north of west. So I just subtract, they divide the magnitude of the displacement by the time. So that takes care of that. Okay, now next we can jump to the distance. How do we find the distance? I need an equation that will tell me the arc length of any random arc. Integral square root of, right? 1 plus the derivative squared, right? But what should we do the derivative in terms of?
dt.
Should it be x prime squared dy or y prime squared dx? I could do both, right? I think for this one, since x is a function of y, it's probably x dx dy squared dy. Right? Is that better? Or should it be which one is easier to do? And then y goes from what? -2 to -2 to 1. Yeah, I think this is better to do. In other words, do the integral as y is the independent variable and x is the dependent, right? and then do the increments dy, and then y goes from -2 to 1, right? And then now you take the derivative of x with respect to y squared. 1 plus, what's dx dy? 2y, so then it's going to be 4y squared dy. Yeah, so square root of 1 plus 4y squared dy integral -2 to 1. Now you put this into your solver again. Not solver, I mean the integral function. You have an integral function there? No? You go to math, function integral, then you put this function, then you put x -2 to 1. The calculator doesn't matter what variable you put here, you can still put x. 1 plus 4x to the power 2 to the power 0.5. Do the integral in terms of x, the limits of the integral, -2 to 1.
6.8.
It's function integral, fn integral.
I got 6.125.
Okay. So 6.125 meters. So now we answer this guy. 6.125 meters. Now, Alan or anyone else, how can we know that we are in the ballpark, that that answer makes sense? How can we know if that answer makes sense or it's completely off? What can we check that against? It's actually on the board.
Plug it back in.
Huh? What is what?
You plug it back in?
No. Compared to what? So this displacement, this distance should be bigger or smaller than what? It should be bigger than the displacement vector's magnitude, right? So this is a straight vector. This distance should be bigger. So what's the magnitude of displacement? 3 root 2. So what is 3 root 2? 3 times 1.414. What is that, 4 point something? Yeah, 4.2, 6.125 meters, yeah. So that's when you smile on the test, you say, I'm headed in the right direction, brother. Yeah.
So you integrated to get the length of the curve, right?
Yeah,
What is that formula? What is that?
the arc length formula, Calc 2. Is that where they cover it, Calc 2?
Yeah.
So right now, who's in Calc 2 now? So have you covered that equation? Probably next chapter.
You can prove that using limits.
Yeah,
You
limits.
just like taking like the little parts and then you take the limit. And
Yeah.
So it's called arc length formula?
Yeah.
It's like chapter 9.
More and more by the fall, when we change to the 101 sequence, get the word out to all your friends and students. We're going to encourage everyone to be in Calc 3 when they take Physics 101. So Physics 101 is going to go all the way deep into gravity. They need to be able to do spherical shells, more integration. So you can't be in Calc 2 anymore. Even though on paper it's still going to say Calc 2. Right? So you need to be Calc 3 with physics. Preferably differentials and linear, but Calc 3 at a minimum. Okay, so now we got the distance. So average speed is next. Simply the distance divided by time. Average speed, distance divided by time, so 6.125 divided by 0.9, and then I can do the average speed. Okay, then what's left? average acceleration, but before we can do average acceleration, we need the ones on the bottom. Initial speed, final speed, initial velocity, final velocity. Then we can do the average acceleration. Okay, so how do I get those ones? Initial speed, initial velocity, final velocity. How do I get those? Well, I need a general equation that will tell me the position of the function as a function of time, right? What's the x position of the function, and what's the y position of the function? So r as a function of t. X of t I hat plus y of t j hat. But that's already given because y of t is given as what? T squared plus 3t cubed minus 2, right? And then x of t is what? Simply the y squared, right? So then that's going to be so this gives me the general position of the particle as a function of time. Now I can differentiate that. It'll give me the general velocity vector as a function of time. So what's the derivative of that? The 2 comes down, right? Then you take the derivative of the inside, right? Chain rule. So then you get 2t plus 9t squared. And that's it. Then the derivative of this. Now, to get the general acceleration vector, you take the what? Derivative of that again. Oh no, right? What's the derivative of that? The product rule, right? So, let's see here. You know what I'm going to do? What if I multiply this in and then take its derivative? Isn't that easier?
Yeah.
Right? I can distribute the 2 in. 9 plus 6 is what? I can add these two. 15 times 2, that's 30. 27 times 2 is 54. Minus 8t minus 36t squared. So all I did is just sort of simplify the v equation a little bit, right? Then what? Now I can take the derivative of that. 12t squared plus 120t cubed plus, what is that? 170 minus 8 minus 72t. Derivative of that. Okay, now that I have the general position function, general velocity function, right? And the general A function, I can simply just put the t's in there, get my initial velocity, final velocity, initial acceleration, final acceleration. That's pretty fast. So what do I put? For initial velocity, what do I put? T is equal to 0 into this function, right? Oh, okay, so the initial velocity in the x direction is, it's actually just 0, right? 0 I hat. And if I put 0 here, 0 j hat. So initially it's not moving actually. So this one, the initial velocity was actually just 0. Okay, how about the final velocity? Then you put 0.9 into here. 0.9, 0.9, 0.9, 0.9. So I feel terribly lazy right now, so you guys do it. It's that time of the day, right?
Yeah.
Okay. Put 0.9 into all that. Anyone got it?
You want to check it?
What is it?
It's pretty big.
Yeah, just tell me what you got.
Negative 2,900.
0.9? Why would it be that big?
Unless
Huh? It should be positive. Because look how the particle here, it can't be negative. It has to be, the x component has to be positive. Did you tell me negative? I already knew something is suspicious. Yeah. Yeah, that makes more sense, yeah. 18.125. Okay, how about the y? Well, y is easy. Just 2 times 0.9 plus 9 times 0.9 squared. Huh? 2, 9.09. So that tells you the direction that it's going, you see? 18 and 9. So it's going faster in the x direction. That makes sense, you see? 18 and 9 that way. So velocity should always be tangential to the path that it's taking. It makes sense. You see? How about the initial acceleration? So then you just put 0 into here. 0, 0, 0, 0, but then we have a negative 8. You put 0 here, you got what? 2. So what does that mean? The initial velocity was 0, but the acceleration wasn't 0. So what does that mean? Even though the particle wasn't moving, there were already forces pushing it in that direction. So what direction were the forces? Negative 8 and 2, so it was some direction like this. You know, initial acceleration. Well, it was mostly in the x direction, something like this. Pushing it like that direction, which is exactly what caused it to move in the first place, right? Because otherwise, how can a particle stand still, and if there's no forces on it, why would it move? So the initial acceleration should be something. That's why the particle moved. You see? You can't get this is 0 and this is 0, then why would it move? See? And then the final acceleration, then you put 0.9 here, and you put 0.9 there. Let's see what we get. Up 0.547, and then 0.9 here. So now those are the forces on it. So that means that mostly the forces are in the x direction. The x direction force is a lot larger than y. Okay, what's left to do? The average acceleration, right? We don't know that yet. What is the average acceleration? Yeah. Change in v over t. So this minus this, right? Which is just simply going to be itself, plus this minus this, which is also going to be itself, right? Divided by t, which is 0.9. 18 divided by 0.9, whatever that is. So 20 something, right? Four? 3?
13.
Huh?
20.13.
013, right? 014, yeah.
No, it's 13. 0.13.
Oh man, I'm doing bad with my mind. 20.13. I add plus. It's gonna be what? 10.1? Yeah? That's meters per second squared. So the average acceleration should be, you see, this number should be in between these two, right? And then 10 should be in between these two. Not exactly in the middle, but somewhere in the middle, right? So we now know the average acceleration, the initial acceleration, the initial velocity, the final velocity. We already know the initial velocity. I think we know everything, don't we? We calculated the average velocity earlier, average speed, initial, final, and average. I think we're done. Okay, so on Wednesday we'll now do the examples of constant acceleration in 2 dimensions. Yeah.
For the displacement function at the very top, you didn't subtract any constants because maybe this becomes 0 when you derive, right?
This one?
That's the left, RG. You didn't add any constants because you didn't,
Why would I add a constant
because
there?
it starts at 4 negative.
That already takes care of that because we already knew that, you see, it starts at -2. And then -2 squared is a 4. So if I put t is 0, this is going to give you 4, and then t0 is going to give you -2.
Oh, okay, so that's just,
It already includes that.
it's the vector in parametric.
Yeah, parametric form, yes. Okay, good job, guys. So go to